Thank you for joining Red Team Village at ActivityCon today. Our next speaker is Rachana, and she'll be covering securing container images and leveraging the Kubernetes CI/CD pipelines in the DevOps world. Don't forget to join us in our channel on the HackerOne Discord server.
Hello, everyone. This talk is on how to continuously deliver a secure Docker app to orchestrators. I'm Rachana Vishwanathula, and I'm a developer advocate at IBM. As part of enterprises IT's digital transformation, applications have expanded from traditional bare metal to virtual machines and now to containers. This is driving containerized app deployment. With that, enterprises are faced with a key challenge: how to ensure that these containerized applications are secure. Containers are standalone, lightweight, portable, and they provide time to market and infrastructure efficiency. They have broad appeal because they allow users to easily package an application and all its dependencies into a single image, which can be promoted to deployment, development, test, production without any change. Containers make it easy to ensure consistency across environments, across multiple deployment targets like VMs, bare metal servers, or public or private cloud. And this helps teams more easily develop and manage applications that deliver business value. And because of this, app modernization and migration to cloud is significantly increasing container adoption. In the next 2 years, 89% increase in container usage is expected. And despite the high adoption rate, container security continues to be the concern for IT professionals. 50% of IT professionals cite security as primary issue with their container strategy. Without sufficient security strategy and security controls, containers can expose organizations to potential cybersecurity risks. So before we get started into the security side of things, let's just understand what is cloud native. Cloud native is nothing but a set of practices, technologies, and architectures. And simply put, it's a combination of automated DevOps, containers, and microservices. Cloud native applications are built using multiple independent microservices that are deployed in cloud environments. That avoids the typical monolith scenario of tangled code or a scope creep or over collaboration, which ultimately impacts the release schedules. Using a DevOps based continuous delivery model, software development teams can quickly and iteratively add new features to an application. DevOps. DevOps is just a combination of cultural philosophies, practices, and tools that can increase organizations' ability to deliver services at high velocity. DevOps is a practice which involves having your developers in the organization and the ops teams working together, so that if there are any changes that are being made to the code base by the developers, and if it's impacting how the infrastructure as a whole is working, that's when the op teams have visibility into it and manage the changes, right? And DevOps also includes a continuous model such that if a developer is triggering some changes, the next steps post the changes, maybe building the code, applying the unit tests, validating some of the test cases. All this can be done in a continuous model using DevOps practices, right? Container security, right? So DevOps isn't just about development and operation teams. If you want to take full advantage of the agility and responsiveness of a DevOps approach, IT security also plays an integrated role in the full life cycle of your apps. DevSecOps means thinking about application and infrastructure security from start. It also means automating some of the security gates to keep the DevOps workflow from slowing down, selecting the right tools to continuously integrate security, like agreeing on an integrated development environment with security features, can help us meet these goals. However, effective DevOps security requires more than new tools. It builds on cultural changes of DevOps to integrate the work of security teams sooner than later. And with this approach, there is a way for us to integrate DevOps and security for best of DevSecOps practicing by installing some of the controls. So if you look at it, you can secure by design, culture, and practice is a successful program uh, with the people culture that lead to best coding practices. Then you have shift left secure design and development, uh, which is nothing but you have to shift left and incorporate security at each and every stage of your SDLC life cycle. In a typical containerized environment, you can't look at security as an afterthought. You can't just look at security as an afterthought and create some patches or firewalls and try to protect your crown jewel from external attacks. Instead, you got to shift left and incorporate security at each and every single stage of your SDLC. That's shift left practice. Then you have enable core security controls early. It simply means we have to implement core controls across the data, identity, network, endpoint, and containers. We have to ensure that the security controls are in place for all the core controls. Then you have continuous testing and validation. We have to validate with offensive testing and on-demand scanning and automation refactoring, which will lead to continuous innovation, continuous delivery, and automation, right? And you can also have your security controls automation. There are tools such as Red Hat Ansible, which establishes a robust DevSecOps toolchain while helping automate the deployment of security controls embedded into the development of new workloads. And here are some of the challenges while securing the containers. There are multiple reasons why security can be challenging for container environments. These are some of the considerations which are very critical in a container environment. Starting with speed of container deployment can be double-edged sword. The benefit of container technology is that they accelerate application development and deployment process, making security updates, upgrades, and vulnerability patching very fast and easy. Yet the speed of deployment can be challenged too. Often there is not enough time for quality assurance or security testing. This means the companies need to go through manual process of consistently checking that the latest versions of containers are the ones that are being used, that all the code is patched and fully up to date. And then you have microservices. Microservices adds complexity. The fact that containers typically require application to be broken into smaller microservices, which results in increased traffic and complex access control routes. You have a lot of services and often many ports. That means there are many doors to secure. Plus, each door has less information about what's going on, so it's harder to identify if someone's the bad guy. So, and then you have use of public container repositories. The traditional software development process, build, test, deploy, quickly becomes irrelevant in the age of containers. In fact, developers can often grab the ready-to-use unscanned images from public repositories and throw them up into the cloud. By the time someone notices that containers are there, they've done their job and they're gone. The life cycle might be over by the time security team can go in. And then you have lack of isolation. One of the nice things about virtual machines is that if an attacker takes over your virtual machine, the damage he can do is limited to that particular virtual machine. This is not so with the containers. An attacker who compromises one container could potentially gain access to others on the same host. The lack of strict isolation between containers is also inherent container security challenge. Then you have lack of visibility. Portability makes containers susceptible to in-motion compromises. Many security professionals don't have the right tools to monitor the transient containers and microservices as they appear and disappear. Additionally, most of the recent attacks started from within the data center and moved laterally due to the lack of visibility and control the east-west traffic, right? Hackers exploit the oversight. Not addressing this traffic flow leaves the organization vulnerable to potential security breaches. And finally, you have cloud-native environments. Cloud-native technologies such as containers, serverless, other microservice-based technologies present real challenges to security teams, especially when coupled with fast-paced DevOps processes, right? Cloud native environments require new approach to security, and the lack of skills and expertise can create challenges. And whether you're using containers to build your application from ground up or porting your existing monolith apps to containerized environment, you need to realize that container environment introduce a unique set of security risks that you should be ready to address from day one. So here are some of the major risks, starting with images. Containers are built using a parent image or a base image. Images are useful for building containers because you can reuse them and reuse the various components of an image instead of building a container image from scratch. However, like any other piece of code, images or their dependencies could contain the vulnerabilities. Then you have registry. For developers, the quickest and easiest way to incorporate standard open source components in an application is to pull the appropriate container image from a public registry. When you do this, you're by necessity trusting the registry to maintain at least a basic level of security regarding the contents of image. Then you have orchestration. The orchestration layer of container security focuses on the environment responsible for day-to-day operations of containers. There are multiple moving parts in the orchestrator, such as Kubernetes. And this makes it more challenging to secure not only because of the number of components involved, but also the way in which these components interact. Some communicate via API, some via host file system. All potential points of entry into the orchestration environment must be addressed. Then you have containers themselves. Besides the entities such as apps and images they hold, containers themselves are often considered vulnerable to security risks through container runtimes that manage the container. A vulnerable runtime could expose all containers it runs and the host OS to potential security risks. And then you have host OS. The OS that hosts your container environment is perhaps the most important layer because the attack that compromises the host environment could provide intruders with access to everything else. These are major risk areas in container environment. And the container environment introduces new threat vectors, right? So container security risks are majorly categorized into compromise of container image or container as a whole, and the misuse of container attack to other containers, right? So these are some of the threat vectors that you observe in a typical container environment, starting from images. You have image vulnerabilities to address, configuration to address. There could be embedded malware in the image, embedded clear text secrets, or untrusted images. Then you have registry. Within registry, you might have to address the insecure connections to the registry. If there are any stale images in the registry, insufficient authentication and insufficient authorization restrictions. You got to, before you pick your registry, you got to check all these points are in place, all these points before you go ahead and use it. And then you get into the orchestration platform. That's where you want to check for if there is any unrestricted admin access, unauthorized orchestrator access, or if there's any poorly isolated inter-container network traffic. And finally, the mixing of workload sensitivity levels. And now the container itself could have runtime software vulnerabilities or unbounded network access, insecure runtime configurations, app vulnerabilities, or rogue containers. And finally, the host OS. It's the large attack surface, or it has a shared kernel, and the host OS component vulnerabilities and improper user access and host file system tampering, things like that. These are some of the threat vectors that the container environment presents us with. So you have to make sure that the security services that you're using should cover all the container risk areas, starting from images. Application images are among key vulnerable areas for security risks in a container environment. These images can be outdated ones, insecure versions of software, applications carrying bugs, those containing hidden malware, and those are loosely configured. Moreover, these images often carry authentication keys and certificates. To address this risk, you will have to perform design validation, detect the configuration defects, and define policies to block the instantiation of unsecure images. Then you have to perform uh, the securing the registry. When accessing from a poorly configuring registry, the access should happen through encrypted and authenticated connections. Also, the registry should undergo continuous monitoring to ensure all the stale images that offer scope to vulnerabilities are clear. We should ensure the audit processes, implementation of secure connections, and develop policies for effective authentication. And then you have orchestration. We have to, in order to secure the orchestration, it is recommended that tight access control to cluster-wide administrative accounts through effective authentication mechanisms, such as multi-factor, just beyond password authentication, or segmenting the containers by purpose, sensitivity, and threat posture provides additional defense in depth. Overall, orchestrated platforms should be configured to features that make them facilitate a secure environment for all the apps that they run. Therefore, it's recommended for us to implement RBAC, role-based access control, policies, and implement proper API controls, and design and implementation of workload security. Then you have securing the containers. The most common security issue with containers occurs when container runtimes that manage containers themselves contain some vulnerabilities. A vulnerable runtime can expose all the containers it runs and also the host OS to a potential security risk. So we should ensure that there is vulnerability management in place, monitor and help control unbounded network traffic, and detect and fix insecure container runtime configurations. And finally, securing the host OS. Host OS is key to a successful container environment. Given the fact that it lies at the lowest level of container architecture, it is more critical target to security threats. A compromise to host OS can lead to compromise of all containers that are running on it, right? So that's exactly why we have to harden and scan host OS at constant intervals, and we have to segregate the host resources properly and use configuration management and effective authentication. So here are some of the best practices within container security. Starting with whitelisting the dependencies, right? So we have to, the dependencies that each containers have, right? It's a trade-off between convenience and security. The solution is let developers be developers. Create a dedicated team to whitelist the approved set of golden base images for developers and manage security services teams, build these security base images for use, right? So here's an example. Instead of, you have to whitelist all the dependencies that are present in your container image itself. And then you have, we at any point in time, we cannot use the root user in the container, right? So this will prevent hackers from doing anything that requires root within your container, right? And it will also, if you're not using the root user in the container, it will prevent hackers from using apt-get to install additional tools that they can use to further exploit your container, right? Here's an example. We'll just put user X in your Docker file after running any commands that require root, right? And then limit your container resources, right? For every container that you're using, you have an option to limit the memory and CPU requirements. So this way we can actually prevent DOS attacks by placing memory and CPU limits on a specific container. Then you have more security options when it goes to Kubernetes. You have to use a non-root user in any security context. And you have to ensure that the policy for read-only file system is set, and you got to disallow privileged escalation. And to expand more on Kubernetes, here are some of the best practices, starting with use IAM to configure role-based access control policies, right? This prevents the insider threats if 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 your organization has a lot of confidential data and you don't want to give access to each and every individual that's working on the certain project, it is up to us to define some of these role-based access control policies and put them in place, right? And we have to use RBAC to define pod security policies as well. And then in the later versions of Kubernetes, in later versions than 1.10, the data that resides in etcd is stored on the local disk of master. Hence, it would require us to encrypt this particular data that's being stored if you don't want to, if you don't want any data at rest to be uh, risky, right? And then you've got to enable TLS on your ingress so that any data that's going onto your apps through ingress is encrypted. And then you have open source tools like Calico, using which you can establish network policies, right? If you have a network anomaly or something, and if you want to set a certain policy on that, you can use some of these tools to set those policies in place. And finally, instead of writing your app config onto in your application code, you can create something called a Kubernetes secret, which is by default encrypted. So you can protect your app config using Kubernetes secrets. And finally, there's an open source project called Istio. It's a service mesh that provides uniform way to connect, manage, and secure microservices. What it means is if your microservices are interacting with each other within the cluster, Istio provides a way to establish mutual TLS and secure communication between your microservices. And now getting into secure DevOps for container workloads. So this is a slide which is just going to show you how a typical DevOps pipeline looks like, right? It's a typical delivery pipeline where you have continuous integration and continuous testing in place. So you have a build, dev, test, app scan, dynamic, and prod phases, and at each phase, that particular task is performed. Build is essentially where you'll get code from multiple sources. If your developers are making any changes to your code base, build phase, it just fetches the new changes, performs some sorts of unit test, and creates an app binary. The dev stage is where you are deploying and parallelly doing the test, so on and so forth. Every time a new change is made to the pipeline, if there is any new changes to the code base that is happening, every change in this particular stage, it is automatically going to trigger the next stages that are followed. So that's a typical delivery pipeline. And this is how DevOps, this is how organizations are using delivery pipelines in their day-to-day applications. So what is content trust and image signing? So when you're transferring data among network systems, trust is a central concern. In particular, when communicating over an untrusted medium such as the internet, it is critical for us to ensure the integrity and the publisher of all the data system operates on. So you use Docker engine to push and pull the images from a public or private registry. Content trust gives you the ability to verify both the integrity and the publisher of data that is received from a certain registry over the channel. So Docker Content Trust provides the ability to use digital signatures for data sent to and received from a remote Docker registry. And these signatures are a client-side or runtime verification of integrity and publisher of specific image tags. So through DCT, image publishers can sign their images and image consumers can ensure that the images that they're pulling are signed. So publishers could be individuals or organizations manually signing their content or automating software supply chains signing their content as part of their release process. So when the publisher who is using Docker Content Trust pushes an image into a remote registry, Docker Engine locally signs the image with the publisher's private key. And when the user pulls this image, Docker Engine uses the publisher's public key to verify that the image is exactly what the publisher created. It also ensures that the image wasn't tampered with and it is up to date. And Docker Content Trust provides a strong cryptographic guarantee over what codes and what versions of software run in your infrastructure, right? Docker Content Trust integrates with something called the update framework into Docker by using Notary. Notary is an open source tool that provides trust over any content. It's like a certification authority. So here are some of the use cases. So if you're looking at an image forgery, right? So there is a public and private key in place. So you have a tagging key that if a hacker got into a network and somehow tampered with an image, when the consumer is pulling that particular image, the signature is not validated, which if the digital signature is not verified, that simply means that the image is tampered with. That's that's one of the cases that we can avoid with Content Trust Docker DCT. And the second one is a replay attack. A replay attack is something where a criminal can eavesdrop onto a network communication, and he purposely delays and resends the same thing with something injected into it. So in this case, there is if the publisher is going to publish the Docker image with a tagging key along with it, right? So when you verify the digital signature, uh, you either, I mean, the minute when there is a replay attack or something in between, uh, you when the consumer is trying to pull that particular image, you clearly see that the digital signature over the Docker image is expired, right? That's when you avoid a scenario with the key in place. And then finally, you have compromised keys. What if the key itself is compromised, right? So uh, it doesn't work that way because we are using two keys. There is a public and private key in place. There is a tagging key and an offline key. We're using tagging key to push the image, and then there is an offline key every time you're pulling the image from the repository. So if there is a compromising keys, the image verification is not done and it's just identified as an untrusted image. And then you have something called vulnerability scanning, wherein we face attack vectors like OS vulnerabilities, or it could be application weaknesses like XSS or buffer overload or SQL injection. With containerization, every layer in the container is just one link in the chain. The containers that you produce can be used as a base for another container, and so on, with every link in the chain susceptible to attack vectors. That's when we perform something called vulnerability scanning. When containers are loaded into the container registry service, they should automatically be scanned by VA scanners, vulnerability scanners. And this assessment consists of a list of common vulnerabilities and exposures. We call it CVEs. And these CVEs are identified with a CVE ID. And CVEs typically include the application weaknesses, or it's a collection of various issues. It's a CVE is a huge directory that already exists. You have vulnerability scanning so that the CVEs are automatically scanned and given out every time you do something. So this is how a typical VA scanner would look like. So every time you scan your image, if there are any application weaknesses in your image, it has to give out the CVE ID, and it will provide the summary of what the issue is. And then you have to get a fix on how to resolve, right? Every time you're going for a DevSecOps pipeline, you have to infuse your VA scan as one of the stages so that you don't have any CVEs in your images, or maybe some of the configuration issues. So if you're setting up a typical DevOps pipeline, which includes DCT and VA scanning, this is how it would look like. You have an initial pipeline where you are setting up image signing. You have two stages. The init Docker Content Trust stage starts by DCT using the information that you provided while you set up the key management instances, right? And this stage also allocates the keys and, manages the keys, right? This is where you're just creating some of the keys. And then you have something called setting up IKS runtime enforcement in the deployment cluster, which it is a stage that is going to create image enforcement policy that is applied on cluster. And this stage is going to just specify that if there is any, if the image that is pulled is not trusted, if you found any different signatures or something, just don't create any deployments for it, right? That's the policy that the stage is going to create. Why have a separate pipeline for these two stages? In future, if your keys are compromised and somehow, you have to have a stage that is going to automatically rotate your keys and perform the next steps, create a policy and apply it on your cluster. And then you have a stage in which you have build, containerize, validate, and deploy. You have your unit tests in place while you're building your code. And then while you're containerizing, instead of building a container image, you're building a securely signed container image. What does it mean is to create using the keys that are created in the previous pipeline, you're building a securely signed image. Then you have a validate stage where you're performing VA scans to get CVEs, or if there are any configuration issues, things like that, and you're checking the vulnerabilities. And again, before deploying it onto the orchestration engine, you're pre-checking the signatures, and then you're going to the deploy stage, right? And meanwhile, the deployment chain could also have vulnerability advisor, Docker image signing, checking source control, issue tracking, online editing, and then deployment Kubernetes, right? So this is this particular stage. This is how it might look like, where if there are any, if you see if there is any vulnerability, if for this particular image it says 173 vulnerabilities and 8 configuration issues are found. So that's when the pipeline shouldn't go through, right? And this assessment is going to obviously have an overall image status based on vulnerabilities, identified configuration issues, and applied exemptions. Some of the attack vectors like OS vulnerabilities and application weaknesses can be recognized in this very stage itself. So that's how you securely deliver a containerized application to an orchestration engine through DevOps pipelines. That's my talk. Thank you.
you.